Welcome back to physics. We are now transitioning into electrostatics and then into electrodynamics and circuits. So what I want to do today is give you a brief overview of some background terminology, and then you're going to move into some calculations and a short investigation dealing with making observations of charged objects. So the basic idea of electrostatics, we're dealing with charges at rest. Now, when we say at rest, basically what we mean is that there's no net or organized motion. In other words, you may have random motions, but there's not a net movement of charges from, say, point A to point B. That would be a dynamic application. A little bit of background: two types of charges, positive and negative charges. And so we have protons, which typically carry a positive charge, electrons, which typically carry a negative charge, or we should say always carry those charges. We'll talk about the amount just in a second when we talk about units. Evidence and observations of charges. Keep in mind that atoms are far too small to be able to see. Even with the best microscope, micro 10 to the negative 6 power uses light of that wavelength to see things in that neighborhood of size. Most of your atoms are 10 to the negative 10th meters in size, which is 10,000 times smaller than the wavelength of light. So we have never ever seen an atom, let alone a proton, electron, or a neutron. So then in this chapter, you have to get used to making larger observations and then inferring what the charges would have to be doing to be able to result in that observation. More as we get into our different methods of charging. Our unit of charge is a coulomb. A coulomb is the amount of charge on 6.25 times 10 to the 18th electrons. So it is a very large amount of charge. Typically, when we are placing charges on objects, we won't deal with entire coulombs of charge. We will use a couple metric prefixes that we have not used too much before this year: microcoulombs and nanocoulombs. The Greek letter mu, that's a symbol for micro, 10 to the negative 6th coulombs. Nano, the small n, 10 to the negative 9th coulombs. So when you're given those units, you'll need to put in that power of 10 in the place of that metric prefix. Back to our electron and our proton up above. A proton has a charge, symbol for charge is the letter Q, of a positive 1.6 times 10 to the negative 19th coulombs. And an electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. Now, when you are charging an object, say you are walking across the carpet and dragging your feet and you build up a charge, the number of charges that are transferred, you're up in the millions, billions, trillions range. Rarely do we ever deal with just single charges that are being transferred. Now, I want to highlight here on these amounts of charge, typically you're going to use that to be able to convert. I could set up a picket fence, and we'll do this in a minute in problem solving, whereby, for example, 1.6 times 10 to the negative 19th coulombs is the amount of charge of one electron. So we could use this to convert from a number of coulombs into a number of electrons, or vice versa. Now, a little bit more terminology. Conductors and insulators. Conductors, these are generally metals, and basically conductors are substances that don't hold on to their outer valence shell electrons too strongly so that they can easily or readily transfer charge. Examples of conductors, again, most metals. So when you place a charge on a metal object, that charge is able to move throughout that object. And if you're transferring a charge, typically in a solid, that's going to be electrons. If you're trying to transfer protons, those are in the nucleus, and that would involve a nuclear reaction. That was a few chapters ago. We're not going to ponder those nuclear reactions here. So typically those protons are stuck in the nucleus, and it's the electrons that are able to transfer. When you have a substance that is an insulator, then basically you have a substance that holds onto those valence electrons very strongly and does not allow charge to transfer easily. That does not mean it won't transfer charge. It can, but usually that means you have to pull those electrons off, which may involve burning through the substance, ionizing the substance, but we'll get into more applications of that. When you place a charge on an insulator, that excess charge, say I dump an extra 1,000,000 electrons on an insulating substance such as wood or rubber or most cloth, that charge is pretty much going to stay where I put it because the atoms cannot transfer that charge. That charge, if I dump it in one spot, it will stay in that one spot on the insulator. If I put 1,000,000 extra electrons on a conductor, those electrons are going to spread out everywhere across the surface of that object. So you need to be able to distinguish conductors and insulators and understand these are not separate categories, but rather extremes. To be able to observe charges, we have to transfer that charge because we can't see electrons and we can't see protons. So there are 4 different methods by which we can charge objects, and you're going to investigate some of these in a few minutes. So I want to give an overview here, and I want to first of all categorize what these apply to. Friction generally only applies to substances that are insulators. Polarization also applies to substances that are insulators. So let's take these 2 first. Friction is what it sounds like. If I take an insulator and rub it against another substance in friction. You take an insulator, you rub it against another substance. That rubbing against causes charges to be pulled off or scraped off the one substance and transferred to the other substance. When you drag your feet across carpeting, you are scraping electrons off the carpeting. Those electrons are passing into and actually doing something called tunneling through the sole of your shoe to be able to be deposited on your body. Your skin overall is an insulator, but the oils on your skin do put a little conductive layer on the surface of your skin. So when you drag your feet across carpeting, you will get a buildup of charges on the surface of your body. Polarization. This is also an insulator. And basically when you have an insulator, what you can have is substances that are polar, substances that have lopsided atoms. By lopsided atoms, we mean the electron cloud and the nucleus are not evenly distributed. So you have an atom, imagine that shape I just drew was an atom, where one side is negative and one side is positive. So then if I have a substance that is polar, or even if I have a substance that is not, I can cause it or induce it to be polar. If I have, say, a balloon here that is positively charged, and I bring it near a second substance that is an insulator right here, these atoms that are lopsided will swivel around and line up. Opposite charges attract each other. These atoms that would have originally been oriented randomly, they would line up where they are, kind of swivel around, so that the negative side of each one would be facing towards the positive balloon. So then on the surface of this, we have polarized it. We have caused a region of charge to build up just by swiveling these atoms around. Now let's consider conduction and induction. Both of these apply to conductors. So, induction. If I have a charged object, and again, I'll imagine a balloon here I'm going to draw a little smaller so I save some room. So here is my charged balloon, and I bring it near an object now that is a conductor. So we'll say that it's metal. Charges are not tightly held by the atoms, so then what happens is electrons actually flow and form a region of charge. There's no contact. Your two substances do not touch, but you just cause electrons to flow from where they were and build up on that side. That would mean elsewhere in the object, you still have the remaining atoms, which now don't quite have as many electrons as they should. So then you have a positive region somewhere else. So then induction is no contact between your two objects, and you have charges that flow and gather in one location. In this case, it's the location adjacent to the balloon. Conduction also applies to conductors. Your only real difference here now is that the objects touch. Induction, there's no contact. Conduction, there is contact. And so then if we touch the objects, then actual charge can be transferred. And so then if I have an object that is charged negatively and I touch it over to a second object, some of those electrons will actually flow from the first object to the second object. So then object number 1, object number 2. If object number 1 has a negative charge, and if object number 1 has a negative charge, and then I bring object number 2 and 1 together and I touch them, what's going to happen here is that charges will transfer. And I will end up with some of those negative charges then moving over here to my second object. They won't all go there. Some of them will, and you will kind of balance the amount of charges on the objects. Conduction and induction apply to conductors. Friction and polarization apply to insulators. I wanted to take a minute to demonstrate charging different objects by different methods. So I have a balloon here. The balloon is an insulator, and I can charge this insulator by friction. So if I take this and I rub it against my shirt, I am scraping charges. One of the substances, either my shirt or the balloon, has more of an affinity to gain electrons. The other has more of an affinity to lose electrons. So I am transferring charges. So the balloon is charged, and I can get it to interact with different substances. For example, and I'm going to tilt my screen down here. On the desk here, I have several pieces of tissue paper that are torn up, and if I bring this over the top of them, it does attract them up. Tissue paper is an insulator, and so what's happening is the charged balloon is polarizing the atoms in the tissue paper to cause separations of charges as we described, and then that separation of charges, so you've lopsided the atoms. Let's suppose the balloon is positive. Then you've lopsided the atoms in the tissue paper so that the negative side of the atoms on the tissue paper is closer to the balloon, causing it to stick. So friction on the balloon and polarization on the pieces of tissue paper. Now, whole sheet of tissue paper here. If I have a whole sheet of tissue paper and I take my balloon over it, I can attract the whole sheet of tissue paper up. I am polarizing the atoms in the tissue paper because the tissue paper is an insulator, causing it to attract. I have a sheet of aluminum foil here, now a conductor. So, tilting you down again, if I bring my charged balloon near to the aluminum foil, and I'm going to take a little bit smaller piece of aluminum foil. Here we have a little bit smaller piece. and I am attracting the aluminum foil. Now, I'm not coming in contact with it, so this is induction. If I come in contact with it, I will actually transfer some of the charges. Now it is sticking there until the charge transfer, and I transfer some of the charges. As soon as I touch it, then that is conduction. Now, when you have charged objects, they will apply forces to each other, and that force we can describe with an equation called Coulomb's law. So let's imagine we have two different objects here. Object number 1, object number 2. Well, each of them is going to have a certain amount of charge. So making sure we have symbols right. Q stands for charge. I will write it as a lowercase q, and I will do it as a kind of cursive so that you can tell it is lowercase. So an object 1 would have a charge of Q1. Object 2 would have a charge of Q2. The electrostatic force, F sub EL. If we want to increase the electrostatic force, we can do so by increasing the amount of charge on each object. The more charge you have, the more they're going to attract or repel. That implies a direct proportion or a linear relationship. The other thing we can adjust here is where these objects are, what distance separates these different objects. And we're going to use an R for that distance. So R is the distance between the centers. If we want to increase the electrostatic force, well, then we're going to have to put the objects closer together. Well, now those things are doing opposite, and so that implies an inverse relationship. So then in the end, if we want to assemble these into an equation, all we need is a proportionality constant. Our proportionality constant is K sub E, and it is referred to as just generally the electrostatic constant. And it has a value of 9 times 10 to the 9th Newton meter squared over Coulomb squared. So if we assemble these all together into an equation to calculate electrostatic force, K sub E, our proportionality constant, multiplied by Q1 multiplied by Q2, divided by R, but it's not just R, it is an R squared. So then electrostatic force is directly proportional to the product of the charges Q1 multiplied by Q2 and inversely proportional to the square of the distance between those charges. Now, let's take a look at an example. We've got an object of net charge positive 3.5 microcoulombs, and we have a second object 9 centimeters away of charge negative 8 microcoulombs. So then we know Q1 positive 3.5 microcoulombs. We know Q2 negative 8 microcoulombs. And we know R, which is 9 centimeters, which we'll need to convert to meters, 0.09 meters. Part A, how many electrons had to be added or removed from the positive 5 microcoulomb object to give it that charge? So we've got positive 3.5 microcoulombs, which is 3.5 times 10 to the negative 6th coulombs. We want to convert that into electrons, so we know that one electron has a charge of 1.6 times 10 to the negative 19th coulombs. So then we'll divide, and we'll get about 2.19 times 10 to the 13th electrons. So that's 21.9 trillion electrons. Whenever you're talking about charge transfers, it is a significant number. Now, we want to know whether we had to add or remove. Well, the object has a positive charge, positive 3.5. The only way you're going to go to positive charge when you are dealing with electrons is if you remove those electrons from the object. Part B, calculate the electrostatic force, Coulomb's law, KQ1, Q2 over R squared. So then our K value, that's the 9 times 10 to the 9th Newton meter squared per Coulomb squared. Our two charges, 3.5 times 10 to the negative 6 coulombs and 8 times 10 to the negative 6 coulombs. Notice I only plugged the magnitudes of the charges in. I didn't plug the plus or minus. We're going to be able to tell whether they attract or repel based on those signs, but it doesn't give us any other information about the force, and that's why I have left those signs off. And then over our distance squared, 0.09 meters squared. When we calculate, that's going to give us a value of 31.1 newtons. One object is positive, one object is negative. Opposite objects attract each other. So then 31.1 newtons, and the vector direction is attract. C, if the objects are touched together, what happens? Well, what happens here is going to depend. What are they? Are your substances conductors? And if your substances are conductors, then charges can transfer. So then when you touch those objects together, the charges will combine. They can't neutralize each other. You have a positive 3.5 and a negative 8. You don't have enough positive charge to counteract the negative charge, but the charges will combine. So then if I take the positive 3.5 microcoulombs and combine it with the negative 8 microcoulombs, that's going to give us negative 4.5 microcoulombs. And that negative 4.5 microcoulombs is then going to distribute amidst your two objects. So then you're going to end up with negative 2.25 microcoulombs on each of the two objects. If they're insulators, then insulators do not transfer charge easily. So then if you touch them together, nothing happens because they cannot transfer the charge. You pull them back apart, they have exactly the same charge they had previously. Now in part D, calculate the force on each object after they are touched together, and we're going to assume on part D that we are dealing with the two objects as conductors. So then similar to part B, F equals K Q1 Q2 over R squared. So then our 9 times 10 to the 9th Newton meter squared per Coulomb squared. Our charges are both 2.25 times 10 to the negative 6th. Our distance is now 8 centimeters, so then 0.08 meters. The biggest mistake people make in using this equation is forgetting the squared in the denominator. Don't forget the squared. So then when we plug those numbers in, we get a 7.12 newtons. Both objects are negative. Those are like signs. Like-signed objects repel each other. So your force is 7.12 newtons repulsive force. Ponder physics.